Please welcome Bart Preneel, KU Leuven.
Hello, my name is Bart Preneel, head of the research group COSIC at KU Leuven, one of the world's leading research centers in applied cryptography and hardware security. I'm proud to nominate our spin-off Belfort for the Falling Walls Science Startup category. Belfort is building breakthrough hardware that allows to process encrypted data without ever decrypting it. Their design solves this long-term standing open challenge by translating deep cryptographic innovations into working scalable infrastructure. It's already deployed in the cloud, tested by early adopters, and ready to scale. Beyond technology, societal relevance of this breakthrough is profound. Belfort allows to process highly sensitive data such as health records or financial information without compromising privacy. This is essential in a world where privacy and trust in digital systems are under pressure. That's why I believe Belfort is a strong contender for Science Breakthrough of the Year.
Breaking the wall of insecure data processing. Michiel van Berendonk. Belfort.
My name is Michiel van Berendonk. I'm co-founder and CEO of Belfort, and we are hard at work solving the data paradox. In today's world, data is increasingly driving value. It's being used to train models, it's being used for inference. We even saw some examples of that in prior preaches today. However, there's also lots and lots of data in the world, valuable data that's currently not being used. This is data that's too sensitive, too confidential to be used publicly. Take, for example, medical patient data. This is data that could be used to further improve patient treatments, search for medicines, all those type of applications, but often too confidential, too private to leave hospital walls. Today, when you're using cloud computing, when you're using tools, algorithms to analyze your data, often you're fully exposing it. Many people have made the error of dropping a sensitive PDF into ChatGPT. There's now images as well. Before long, there will maybe be tools for medical diagnosis. All of the data is exposed. Sometimes, depending on the provider, it's even being used to train upon. What we're doing at Belfort is computing on encrypted data. This is a new encryption technology where you can encrypt the data, you can secure it, but you can still analyze or process it directly in encrypted form. Whoever is doing that analysis, whoever is processing the data, they never actually see the data that's inside. This offers value, privacy, and security, all three at the same time. Why this is not widely used yet today is that the main drawback of encrypted compute is the cost. When you're using this today, you're making your applications much slower and much costlier. The simple matrix multiplications that you might be used to, they get replaced by very complex cryptographic number theoretic calculations, which the current compute infrastructure of the world cannot handle very well. And that's exactly what we are tackling at Belfort. We are building the world's first chips for encrypted compute. And we're already doing that today on programmable chips. These are devices we can buy where we can program our Belfort executable into these chips. We have an ambitious roadmap, though. Eventually, we want to manufacture our own chips for encrypted compute. This will make encrypted compute massively cheaper, massively faster, massively more energy efficient, which we feel will be essential to open this for many applications. We're just getting started. In fact, we spun out of the university only 2 months ago, but something I'm very proud to say is that we already have a first product live. We're doing this by working with the programmable chips on Amazon Cloud. These are chips that you can rent just like any other cloud instance. You program them with our Belfort executable, work together with a software library, and this is ready to accelerate your encrypted calculations today. The business model we're using here is that you pay per usage. So for every analysis, for every calculation you're doing, you're paying for the use of the hardware. The markets we're going after and our go-to-market strategy is with a first focus on blockchain. That is where there's the first early adopters, where there's the very technical people that have the affinity to integrate this complex cryptography. But we see it much more broadly than that. The large markets we're going after are finance, government, healthcare. All markets where there's sensitive data being processed that holds lots of value, for example, in fraud analytics, in defense, intelligence, and in healthcare. It's about medicine analysis, it's about patient treatments. And those are the markets where we feel the hardware will be necessary to open this up. In blockchain, we're going after the first customers already today, and we're far advanced in talks there. In finance, we've already done a first proof of concept with the payment network SWIFT, where we analyzed encrypted bank transactions. We have a world-class team to work on this, and what really sets us apart is this affinity we have with both the mathematics and the hardware. We can really bridge that gap of translating the very complex cryptography into real-world chips. Our team combines both academic expertise as well as entrepreneurial expertise, and we feel we have the exact mix to tackle this problem. We also recently completed our first funding round and spun out of the university, and we got a great mix of deep tech investors on board to further tackle this. What we're now doing is first going to market on these programmable chips that we have. Second is building the proof of concepts and the applications across government, healthcare, finance, and finally taking the first steps and kickstarting our roadmap towards a dedicated chip. That's the wall we're breaking at Belfort, the wall of insecure data processing, and our vision is to enable a future of encrypted compute. Thank you.
Fantastic. Let's go for the questions. We start with Luca right now. Yes, first row. Thank you very much.
Thank you. When you say you want to build your own chip, do you mean you're building on existing technology and just changing a little bit the architecture, or it's a different kind of chip?
It is a standard digital chip, but what's fundamentally different is the architecture that we design. If you're looking at the compute infrastructure today, for example, GPUs, they're built for matrix multiplications, they're built for floating point arithmetic. What we need in cryptography is very, very different. We work with large integers, we work in polynomial number fields, very different things from, for example, AI processing, and that's why we develop dedicated architectures. But it's with standard technology, standard digital chips that we can tape out at standard manufacturing agencies.
Cyriac, second, please.
So if you get multiple sources with different types of encryption mechanisms, or you don't even know which encryption mechanism they used before to encrypt the data, does this still work, or do you need to have a uniform system behind it?
This works, but that's where we typically need to add functionality on top of it. There's functionality that we can use to transform existing encryption into this homomorphic encryption. That's an operation called transciphering, for example, fully possible. There's also functionality possible where we combine data from multiple sources. That's called multi-key, multi-party homomorphic encryption. So all of that is possible. Typically, some of this comes with additional overheads.
We had Inga as the third question. You have to agree between yourselves here, right? There is a corner of questions.
Perfect, thank you. So who is your main competitor?
Our main competitor is actually not other companies working in this space, I would say, but other technologies. There's alternatives. There's, for example, confidential computing is becoming quite a big topic these days as well. Why we feel this thing will win out versus confidential computing is that the only thing you need to trust here is the mathematics, the encryption, the cryptography. With confidential computing, you're also trusting the hardware provider. You're trusting that they built this thing correctly. You're placing your trust in how the hardware is processing the data. And with confidential computing, what we're seeing time and time again is that these systems get hacked. The secrets get infiltrated. The data gets exposed. There's many flaws and many things to overcome there. What homomorphic encryption, what this encrypted compute has as the main drawback is the cost. And what we very fundamentally believe in is if we can get this cost down, if we can build our hardware, this is the technology that will win out.
Next question then, Iris.
Thanks. What are some of the adoption hurdles that you see when planning to work with some of these very conservative parties like the government and the medical industry? And what's your battle plan to win them over?
Yeah, I would say the first adoption hurdle across all industries is still the speed of the technology. It's a bit of a chicken and egg problem there where the applications are not there yet because the speed is not sufficient. But at the same time, there's very few companies like ours looking into speeding up the problem because the applications are not there. So that's definitely the first hurdle we need to overcome. And one of the ways we're tackling this is by first working with this programmable hardware. Beyond that, government, healthcare, of course, indeed, those are sectors known where there's long adoption cycles, where sales are difficult. We're approaching that step by step. We're really first proving out the fundamental technology with this go-to-market in blockchain and in simpler finance applications. And we feel government, healthcare will follow once the speed-ups are there and also once standardization and maturity of the technology has moved further.
Great. Next question. I have a question for you. And I have a couple of seconds more because I think you deserve a bonus, right? So, do you know what they said in the video before? Why you're so great?
I do.
Let's don't be
I
ashamed.
don't
Tell
know it
us.
out of the top of my head. I think what really sets us apart is what I've also mentioned in the pitch, this combination we have between the cryptography and the hardware. And Bart Preneel, the professor introducing us, he's the head of the research group that we spun out of COSIC. And that is really what sets this research group apart, I would say. It's one of the few cryptography groups in the world that's based in the electrical engineering department instead of with the mathematicians or the computer scientists. And that's exactly what you need to build this combination and to build this expertise that we have in the team.
I think it's great. Now we know why you're so great. At any case, thank you so much for the questions and answers.